Hello, in this video we're going to go over the proof of the Cauchy Mean Value Theorem and one very useful application of this theorem. If you recall, last time we proved the mean value theorem. Mean value theorem told us that if you take, so I'm going to write it down on the right, if you take a function under some certain conditions that it is continuous over the closed interval and differentiable over the open interval, then there is some c that f prime of c is equal to f of b minus f of a over b minus a. And the way you could interpret that was that if you look at the graph of the function, the average rate of change is the value of some is the instantaneous rate of change at some point. Now, and this was the graph of x, the function y in terms of x, and this is y equals f of x. Now, if you look at the graph of two functions in terms of each other, let's say you have a function f and you graph the function f in terms of another function g. Then the way you can think about this one is the average rate of change would be f of b minus f of a over g of b minus g of a. This would be the rise over run. And then the slope at this point, when you are taking the derivative of f with respect to g, it would be derivative of f over derivative of g. So it makes sense that there should be something similar for two functions rather than one function, and the other function is basically the function x. So if you replace the derivative in the denominator, if you replace 1 by x prime, this is essentially then extension of the mean value theorem. Okay, so let's first see what the theorem tells us, and then how do we prove that. Suppose the functions f and g from closed interval ab to r are continuous, and their restrictions to the open interval ab are differentiable. Moreover, assume g prime of x is not 0 for all x inside the open interval. Then there is a point c strictly between a and b inside the open interval for which f of b minus f of a over g of b minus g of a is equal to f prime of c over g prime of c. Okay, so let's see how we can prove this one. If you try to turn that into some form of a Rolle's theorem identity, what you need is for a function f that f of b and f of a are the same, and that tells us that there is some c that f prime of c is equal to 0. If we write down the given equality, so this is going to be my scratch work, and then hopefully we can get it to a complete proof. If we look at this fraction, if we cross multiply, we can write it down in the form of f of b minus f of a times g prime of c minus g of b minus g of a times f prime of c equals 0. So if I find some function whose derivative is this side, and then I show that this function has the same value at the endpoints, then I would be done. And of course, this is the derivative of f of b minus f of a times g of x minus g of b minus g of a times f of x. So if I take this function and I show that this function has the same value at a and b, then by Rolle's theorem there would be a point in between that this is 0, and then I would be able to solve the problem, which is why I'm going to start with this function. So define some function h from ab to r by h of x equals f of b minus f of a times g of x, this is exactly what I have down here, minus g of b minus g of a times f of x. Since both f and g are continuous on the closed interval AB and differentiable on the interval open interval AB, so is H. So H is a continuous function over the closed interval and differentiable over the open interval. Now let's evaluate H of A. H of A is f of B minus f of A times g of A minus g of B minus g of A times f of A. So that is H of A. We're going to multiply this out. We get f of B g of A. We have f of a g of a here, and we also have another f of a g of a here. One of them is negative, the other one is positive. So this is minus g of b f of a. This is h of a. Let's look at h of b. H of b would be f of b minus f of a times g of b minus g of b minus g of a times f of b. Both of these again have a term in common, and that term is f of b g of b. So here I have f of b g of b in the first parenthesis, and the other one has minus f of b g of b in the second parenthesis. So then I would get minus f of a g of b plus g of a f of b. And if you compare these two, you realize that in fact they are the same. Therefore, h of a is in fact equal to h of b. Both of them are f of b g of a minus g of b f of a. They are written just in a little bit of a different format. So now that I have a function that is continuous over the open interval, over the closed interval, and differentiable over the open interval, and it has the same value at the endpoints, I can apply the Rolle's theorem. By the Rolle's theorem, there is some point between A and B such that h prime of c is equal to 0. Now, take the derivative of this function. We get f of b minus f of a times g prime of c minus g of b minus g of a. This is just the function that we defined at the beginning. Evaluated at c must be 0. Now all I need to do is to do a little bit of manipulation. I need to, if you compare this with what we had at the beginning, we had a fraction. So I need to make sure that the denominators aren't 0. Well, we are told that g prime is not 0. So therefore I can divide by g prime of c. But how about g of b minus g of a? Can that be 0? If it could be 0, then that's going to be problematic. So note that g prime of c is not 0 by assumption. Also, if g of a were equal to g of b, then by the Rolle's theorem, g prime of x would be 0 for some x between a and b. That means g of a is not the same as g of b. So now we can rewrite this as f of b minus f of a g prime of c is equal to g of b minus g of a times f prime of c. This guy is non-zero because we just showed that g of a and g of b are not the same. This guy is also not 0. We also discussed why g prime cannot be 0. That was actually the assumption. So if you just divide by g of b minus g of a times g prime of c, you get exactly this. and that's exactly what we needed to prove. Okay, so this is an extension of the mean value theorem, which in turn is an extension of the Rolle's theorem, but all of these can be proved using the Rolle's theorem. Okay, great. So this was a very important theorem. This is a very important theorem, but perhaps even more important than the theorem itself is this corollary of the theorem, which I state that as a theorem because it's actually a very fundamental theorem. And I will show you one application of this theorem. But we will see a lot more of this theorem later when we talk about Taylor polynomials and Lagrange remainder theorem. Let I be an open interval and n be a natural number, and f from I to r have n derivatives. Suppose at some point x naught, all of the derivatives of f from the 0th derivative all the way to the n minus first derivative are all 0. So f of x naught, f prime of x naught, all the way to fn minus 1 of x naught are all 0. Then for each x in I, you can write down f of x as fn of z over n factorial times x minus x naught. Okay, so let's see how we can prove this. We're going to apply the previous theorem, the Cauchy Mean Value Theorem, to the function f of x and x minus x naught to the power of n. So let g of x be x minus x naught to the power of n. We will use the Cauchy Mean Value Theorem for functions f and g over the interval x to x naught or x naught to x, depending on which one is larger. If x is larger, then it would be x naught to x. If x is smaller, then it would be x to x naught. Okay, so what we know is this. We know that there is some, perhaps I will call that C1, inside the one of these intervals, although it has to be inside the open interval, strictly between x naught and x, such that f of x minus f of x naught over g of x minus g of x naught is equal to f prime of x, or c1, over g prime of c1. Now notice that if you look at the derivative of this g prime of x is equal to n x minus x naught to the power of n minus 1, which is n 0, over that interval x naught to x or x to x naught. Now if you plug in the values of f of x naught equals 0 and g of x naught equals 0, we get f of x over g of x equals f prime of c1 over g prime of c1. G prime of c1 is exactly n c minus x naught to the power of n minus 1. Okay, so this tells us f of x over f of x naught is equal to that quantity. And I can replace g of x by the value that I want, by the quantity that it is. So x minus x naught to the power of n, and that's equal to f prime of c1 over n times c minus x naught to the power of n minus 1. Now, if you look at this function, let me actually keep that as g prime of c1, because I'm actually going to repeat the same argument. Okay. Now, I'm able to repeat this process. Note that again, f prime of x naught is also 0, and g prime of x naught is also 0. Thus, f prime of c1 over g prime of c1 is going to be f prime of c1 minus f prime of x naught over g prime of c1 minus g prime of x naught. And this is going to be equal to, we apply the Cauchy mean value theorem again. So it's f double prime of c2 over g double prime of c2 for some c2. So we can repeat this argument again. And then eventually we obtain the initial fraction, which was f of x over x minus x naught to the power of n is equal to fn of cn over gn of cn. But nth derivative of g is n factorial. So n times x minus x naught to the power of n minus 1 is the first derivative. The second derivative is n times n minus 1 times x minus x naught to the power of n minus 2. So the denominator becomes fn, and the numerator remains the same. So this means f of x is in fact fn of cn over n factorial times x minus x naught to the power of n. And that's exactly what we wanted. We wanted to show f is in fact equal to that. Okay, so this completes the proof of this theorem. We just repeatedly apply this exact same theorem, the Cauchy mean value theorem. Next, we are going to look at an example that uses the previous theorem. Consider the function f from 0 to infinity to r, the non-negative real numbers to r, defined by square root of x plus 1 minus 1 minus 1 half x. Show that for all x positive, there is a c inside 0, comma x, for which f of x is equal to negative 1/8 c plus 1 to the power of negative 3 halves times x squared. So let's look at f and evaluate f of 0. So if you look at f of 0 is going to be 1 minus 1 half minus 1, which is 0. Let's look at f prime of x and evaluate f prime of 0. So note that this function can be extended to all values from negative 1 to infinity. So let me actually specify that. Note that f is differentiable even over negative 1 to infinity, because from open negative 1 to infinity, the function is a polynomial square root, and square root is a differentiable function. It's a composition of square root and polynomial. So it is differentiable. So let's evaluate f prime of 0. F prime of x is 1 half 1 plus x to the power of negative 1 half, and then minus 1 half. So that means f prime of 0 is in fact 0. Let's evaluate f double prime of x. F double prime becomes, so going back and looking at what we had, Yeah, so that's what we have. We get -1/4 1 plus x to the power of -3/2. Of course, -1/4 times 1 plus x to the power of -3/2 isn't 0 at 0. So we can apply the theorem before. By theorem, the theorem that we just proved, 5.13, there is some z between 0 and x such that f of x is equal to f double prime of z over 2 factorial x minus x naught. So x naught is 0 here, squared. And that's exactly -1/8 1 plus z to the power of -3/2 times x squared. And that's exactly what we have here. So perhaps I'll change z to c to match what was given, although it doesn't really matter. Okay, so this tells us that f of x is equal to that. So part B of this, we're going to use part A and prove this. So if you look at c, c is between 0 and x. So that means 1 plus c is positive or more than 1, which means 1 plus c, if I raise it to a power of a negative number, it would be less than 1, which means these are properties of inequalities. -1/8 1 plus c to the power of -3/2 is going to be greater than -1/8, which means f of x, if I just multiply by x squared, is greater than -1/8 x squared. Now replace f of x by what they gave us. F of x was root x plus 1 minus 1 minus 1/2 x. That's greater than -1/8 x squared. And this implies root x plus 1 is more than 1 plus 1/2 x minus 1/8 x squared. And that must be exactly what they gave us. Minus, yeah. So that's an application of the Cauchy Mean Value Theorem. Okay, so this brings me to the end of this video. So we are going to continue with this topic in the next video. And if you would like to continue with this, with advanced calculus topics, proof-based advanced calculus topics, feel free to subscribe. And I will see you in the next video.